All right, hello everybody. Welcome to our next CU Prime Talk. Can you go back to the slide before this one? So if this is your first time coming to a CU Prime Talk, we are a group that is in the physics department promoted to diversity and equity and inclusion and building community within physics and other related fields. And one of the ways we do that is through this bi-weekly talk series. So we invite grad students like Shane here to come in and give jargon-free talks about their research or things related to it. So if you are here in the room, we have pizza for you. Make sure you eat all of that up. Be sure to sign in on the laptops if you have not already. And if you are joining us on YouTube, then welcome. We don't have pizza for you, but you can get food yourself. All right. So if at any point you guys have questions, feel free to interrupt and Shane will be sure to take those. If you have questions on YouTube, you can also type those in and we'll be sure to get to those as well. And if not, there are no other questions right now, then we will go ahead and get started. So we'll welcome Shane.
Thank you everyone for coming. I'm Zhang. Today I'm going to share some ideas about towards understanding Earth's climate. First, who am I? I put a question mark here because I think there are many random factors and information that I received that have influenced my decisions in life. But anyway, I'm a fifth-year PhD student in the physics. My research is mostly focused on seismology. I work in Reservoir Group. And the picture here gives you an idea of what seismology is about. Showing the left here is the Earth and the interior structures of the Earth. Imagine there's a south in the North Pole, such as an earthquake, and waves will be propagating from the source through the interior of the Earth. And the surface of the Earth will move as response to the source. And these motions on the surface can be picked up using instruments, as shown in the right here. As these waves travel through the Earth, they are changed by the properties of the Earth, such as temperature and conversations. And my research is to use these waves received on the surface of the Earth to study about the properties of the Earth's interior. I did my undergrad in geophysics at Wuhan University, which you probably know where the city is. So I think one of the reasons I choose to go to Wuhan University is has influenced me particularly in making decisions, which is, as shown here, the foundation series by Isaac Asimov. I used to read lots of science fictions in high school, and the foundation series proposed a theory called psychohistory, which argues that the human civilization, the behavior or the future of human civilization can be predicted using mathematics. And this book motivates me to seriously consider psychology as a major for my undergrad. No, I can't. It works. Okay, so let's start talking about climate. First, let's take a look at some of the most striking observations of climate. So typically, we think about physics as theoretical physics and experimental physics. But it turns out in certain fields of study, such as climate, we cannot really do experiments on the Earth. So the way is that we use computer models to simulate the Earth and compare the simulations with the observations. The figure shown here shows the temperature anomalies during the last 1,000 years. The line here shows the best estimate of the temperature, and the shading shows the uncertainties of the estimates. We note that in recent decades, there's a sharp increase in temperature about 1 degree centigrade, or about 2 Fahrenheit. And since 1850, we have direct observations, measurements of temperature. That's why the uncertainties are smaller here. And before 1850, we have to rely on proxies to reconstruct the temperatures in the past. That's why the uncertainties of temperatures are larger. We also observe an increase of carbon dioxide, or CO2, in the atmosphere over the recent decades. Here shows the carbon dioxide concentration in the atmosphere from the 1960s until present. It increased about 30% over the past half century. One of the major goals of today's talk is to understand how the increase in carbon dioxide is connected to the change in temperature of the Earth. This year's Nobel Prize in Physics is awarded to Suki Manabi, Klaus Hasselmann, and Giorgio Prezi for their contributions to complex systems. My talk today will focus on the work of Manabi and Hasselmann, since their work is more directly related to climate science. To quote Manabi, climate models have become the most powerful tool, not only for predicting climate change, but also for understanding it. Manabi, it seems that the first and foremost goal is to understand climate, which is the motivation of this talk. Since we are interested in temperature, it will be helpful to take a look at how it can be transferred. It turns out there are 3 basic ways that heat can be transferred. Imagine there's a campfire here, and if you put your hands above the fire, you can feel the hot air rising above towards your hands. And this is because when the air is heated up, its density becomes smaller and become lighter, so it's tend to rise up. This way of heat transfer by the motion of air is called convection. And if you put a metal rod near the fire, you will see that the colder end of the rod is heated up as it glows. And the heat will propagate from the hotter end to the colder end by the collision of the molecules. And this way of heat transfer through the collisions of the molecules is called conduction. And finally, if you're standing some distance away from the fire, you can still feel the heat radiated from the fire, just as you feel warm when the sun shines on you. And this way of transfer through light is called radiation. Speaking of radiation, it turns out most of the energy to the Earth is from the sun. So let's first take a look at how will the sun affect the climate of Earth. Shown here is the input energy from the sun, denoted by the symbol F. So we can read the symbol as the downward energy flux from the sun. And the Earth, as any body which has a non-zero temperature, we also emit energy. And we denote energy emitted by the Earth upwards as the symbol like this. If the temperature of the Earth does not change with time, the energy output from the Earth has to be the same as the energy input from the sun. So we can put the terms equal to each other. And because the energy output from a body is related to its temperature, we can infer the temperature of the Earth by the energy it outputs. It turns out in this case, the temperature of the Earth will be 5 degrees centigrade if all of the input energy from the sun is observed. In reality, however, only part of the energy will be absorbed and some will be reflected by clouds and ice. If we consider this energy are reflected by a fraction denoted by alpha, then we can write a new energy balance equation that the energy output from the Earth is the same as the input energy from the sun reduced by a factor of alpha. And because the energy output from the Earth is reduced, its temperature must also reduce. And now the temperature of the Earth is only minus 18 degrees centigrade. As a reference, we observe that the average surface temperature of the Earth is about 15 degrees centigrade. So now, let's assume that the greenhouse gases are added to the atmosphere. And we assume that greenhouse gases can absorb all the energy emitted by Earth. The question I would like you to think about is, how will the addition of greenhouse gases affect the energy balance? And how will the energy balance imply for the temperature? Please feel free to discuss with your neighbors. All right. So anyone want to share some thoughts with us?
Isn't that just the greenhouse gas translate heat release that they cannot be stable?
So you're saying the heat is trapped in the atmosphere? Is that...
Yes.
Yeah. And so how will that affect the temperature?
For the entire country. But that's what happens like humans. Like during the I don't know, like there's some period where we cover the temperature where it's practically over like Celsius, like the entire water.
You're saying which? You're saying that both the surface and the temperature will increase?
Temperature. The surface temperature, the entire climate will be increased. So basically, you have this temperature will get heat. But if you just measure on the surface of the Earth, there's a lot of factors that's affecting the surface of the Earth.
Okay.
If you measure the atmosphere, that temperature will definitely rise.
Okay. Any other ideas? Yes. Mm-hmm.
So they absorb all the
Mm-hmm.
it will be absorbed every time. Not just Europe.
So I think the surface temperature will decrease. Is that what you said?
Well, if the EHD are the ones that take all the heat, and they are, and in this case, they are absorbed all the other 1 year by year. It means that energy will stay the
acid, does it actually absorb or does it like bounce off and stay in the surface or sort of like being emitted out of the atmosphere?
Yes, so here we assume that the greenhouse gas absorb all the energy emitted from the Earth, but itself also have to emit energy because it has a non-zero temperature. All right, so I think what we have just discussed contains the basic idea of the effects of greenhouse gas. And let's see how does the math work out to get some numbers here. And again, we can consider the energy balance as we did before. First, we can consider the energy input, output above the atmosphere. So because the only way for heat to leave the Earth is from the emission of energy from greenhouse gas upward, it has to be the same as the input energy from the sun, as shown by this equation. And if we consider the atmosphere, the input is from the emission from the Earth, and the output is both the upward and downward emission from the greenhouse gases, as shown by this equation. And on the surface of the Earth is emitting energy, is gas energy from the sun, and also from the downwards emission from the greenhouse gases, shown by this equation. If we solve these equations, we find out the flux emitted by the Earth has to be this number, which if we consider with the case before without greenhouse gases, we see that they differ by a factor of 2. It's shown by here. And because the higher the temperature of a body is, the more energy it emits. This means that the temperature of the Earth will also be larger. Here just show the numbers for the flux. And it turns out with greenhouse gases, the temperature on the surface of the Earth will be 30 degrees centigrade. And this number is much larger than we observe, which is, as just said, 15 degrees centigrade. This is because we assume all the energy emitted from the Earth are absorbed by greenhouse gases, while in reality, only part of the energy is absorbed. And if we take that into account, as we will show later, the temperature on the surface of the Earth will be pretty close to 15 degrees centigrade. So we note before that without greenhouse gases, the surface temperature of the Earth is minus 18 degrees centigrade. So greenhouse gases make a difference about 33 degrees centigrade. When we hear about greenhouse gases, we often think about air pollution, but it turns out without greenhouse gases, the Earth might be too cold for humans to even exist. And when we hear about greenhouse gases, it's often linked with carbon dioxide or methane, but it turns out water vapor is the most effective greenhouse gas. Here I will show you how. We know that light is composed of lights from different wavelengths, such as white light can be composed of lights at different colors. And this idea can be generalized. So this picture shows the energy of solar light, of light from the sun at different wavelengths. We say that the sunlight has the most energy at the wavelengths that can be seen from human eyes, but it also has energy at wavelengths that cannot be seen by eyes, such as the shorter wavelengths X-rays or longer wavelengths microwaves. And this dips in the energy of solar light is due to the absorption of solar light in Earth's atmosphere. And shown on the right here is the outgoing energy from the Earth. We also see that there are dips in the outgoing energy, which are due to absorption by greenhouse gases. In the bottom here shows the absorption of light from water vapor and also from carbon dioxide. So these dips in the outgoing energy from the Earth corresponds to the absorption by water vapor. And because water vapor can absorb energy in more different wavelengths and in a larger fraction, it is more effective to absorb energy emitted by the Earth, and hence a more effective greenhouse gas. If you say go to a 14er, you're probably gonna take some clothes because the temperature will be lower when you go to the top. And you might heard that the temperature will decrease about 6 degrees centigrade with elevation gain of 1 kilometer. It turns out if we consider only the radiation as the way of heat transfer, then the temperature will decrease much faster with elevation to be 15 degrees centigrade per kilometer. As we talked before, there's two other ways for heat transfer, and one of them is convection. And here shows how convection might work for the Earth. So when the surface of the Earth is warmed up, the air becomes hotter and they become lighter. So they would like to rise above. And as they rise, their temperature decrease. They will condense to raindrops and in the process release heat. To consider this effect of air convection, we can get the correct decrease of temperature with elevation about 6 degrees centigrade per kilometer. And as we just said, water vapor is an effective greenhouse gas. So with the increase in the temperature on the surface, more water vapor will come to the atmosphere. And as water vapor can absorb energy emitted by the Earth, they will cause further warming of the Earth. It turns out this feedback from water vapor can roughly double the effect of global warming. So without water feedback, an increase of temperature in Earth will be half times lower. And here shows the prediction of temperature from averaged over the surface of the Earth, from the surface to the atmosphere. 3 lines are shown here, and the blue line is for a carbon dioxide concentration of 150 parts per million, and black line is 300, and red line is 600. This is the prediction made by Manabe and colleagues in the 1960s. They predict that with a doubling of CO2 in the atmosphere, the temperature in the lower atmosphere of the Earth will increase about 2 degrees centigrade. However, the temperature in the upper atmosphere will decrease with the increase of CO2. And we will talk more about this prediction later. So how you might wonder, how does the prediction compare with observations? So here is the prediction made in the 1980s of the change in the surface temperature of the Earth by doubling CO2 in the atmosphere. the yellow color means it gets warmer, while the blue color here means it's getting colder. First, we say that most of the surface of the Earth is warming by prediction. And more warming happens in the northern hemisphere than in the southern hemisphere because there are more land in the northern hemisphere, but more oceans in the southern hemisphere. And we know that water has a larger heat capacity, which means that given the same amount of heat, water will increase temperature smaller than the land. And we also say that temperature increase more in the land than in oceans, such as in North America and Eurasia. And in the right here shows the observations from 1961 until 2015. It's remarkable that the general patterns of temperature change is very similar to the predictions made almost 3 decades ago. So far, we have talked about the basic physical processes of the Earth's climate, but you probably know that weather seems very hard to predict, and how will that affect our prediction of climate? To quote Lawrence, climate is what you expect, and weather is what you get. Weather is hard to predict, primarily because it's chaotic. By chaotic, I mean a deterministic system that can be perfectly predicted given initial conditions. However, if it's chaotic, then small errors in initial conditions may cause totally wrong predictions. I would like you to think about how do you define climate and weather. And since weather seems chaotic, is the prediction of climate even possible? For instance, what can you say about the weather of Boulder in 2 weeks? And how about the temperature next July compared to this November in Boulder? Please feel free to discuss with your neighbors. All right, so does anyone want to share ideas with us? Yes.
Okay, so the weather, it's like change the atmospheric conditions by for example, you can have the weather like sun, it's cloudy, it's raining, something that happens day by day. Like the case for climate, it can be something that actually belongs to the conditions. For example, if you go to tropical, the climate is going to be expected to be sunny, warm. So that would be like the definition.
Okay, so you're talking about weather being more short-term like and climate being more long-term and maybe larger in space. Something you expect to happen. Okay, yeah, that's what Lauren said. The climate is what you expect. Cool. Yeah.
So I guess the thing that, well, I guess the 3 of us had formulated was that weather is, well, in the short term, weather is like, as you have a very small time scale, weather is very predictable. Like in the next 10 minutes, I know that you can be pretty certain that nothing's going to happen to change the weather. But as you expand the time scale a little bit toward it for weather, it gets more and more unpredictable as like little changes in your initial conditions propagate outwards.
Right.
But for climate, you can think of it more like I guess you might think of it like the electrons in a wire,
Mhm.
where they're all moving around in various directions with a lot of uncertainty. But if you put a voltage across them, the very small net movement ends up pushing it all towards
Mhm.
something, pushing it all towards some end goal and state. I guess.
Awesome. Yeah, that's actually what I'm going to talk about next. So thanks for the explanation. So I think we are all talk about the importance of time scales of with and perhaps also space scales in defining climate weather. So let's put what just said. Why do we say that weather is chaotic, and what does this sensitive to initial conditions mean? And weather is probably chaotic, which is also known as the butterfly effect. As Lawrence puts it, can the flap of wings of a butterfly in Brazil cause a tornado in Texas? And Lawrence was considering the same process we just talked, which is the convection of air in the atmosphere. For instance, let's imagine that a particle in the atmosphere is moving around and is plotting this beautiful two-lobe trajectories, which looks like a butterfly. And now we consider two particles. Starting at a slightly different initial position, they differ only by 1 part in 10,000. At first, they almost have exactly the same trajectories. But as time goes on, the trajectories become more and more different. And we can plot the positions in the x direction with time. We can say before time about 25, the positions of the two particles almost overlap each other. However, after time about 25, their trajectories diverge. So it's indeed hard to predict weather, since weather is sensitive to the initial conditions. However, if we take a look, if we count the number of times a particle is at a certain position, we found that the two particles have a similar distributions in their positions. This can be seen from this two-lobe structure of their trajectories. In fact, if we consider the distribution of their positions over a longer period of time, they will have a more similar distribution in positions. This suggests that climate, which is statistics of weather or summary of different samples of weather, is probably not chaotic. But is it another way to directly introduce variability into climate models? This idea is first proposed by Hasselmann in the 1970s, which is inspired by Brownian motion. As one of you just said, the electrons are moving randomly due to thermal motions. And the Brownian motion considers that imagine a pollen particle is in the water, and you use a microscope to see the movement of this yellow bigger particle. We will say that the smaller water molecules are moving very fast, and they collide with the bigger particle and cause it to move around. If we plot the motions of the smaller particles as blue lines, we say that they move very quickly. And if we plot the motion of the bigger particle as orange lines, we say that it moves much slowly with time. And this has inspired Haussmann to propose that weather is changing much faster than climate. And the climate can be modeled as the response slowly to the fastly changing weather. To be concrete, the top here shows an example of the variations in the heat flux on the sea surface with time. These variations changes very quickly with time. In the bottom here shows the variation of the temperature of the ocean at a depth of 500 meters, and it varies much slowly with time. So we have talked about basic physical processes and how climate and weather are connected. Then you might wonder, how do we detect and attribute change in climate to human or natural causes? To rhyme with what Lawrence said, Alan said that climate is what you affect and weather is what gets you. The idea also proposed by Haussmann in the 1970s is to look at patterns in the change of climate, just as we use fingerprints to uniquely identify a human being. To be concrete, let's consider the average temperature on the surface of the Earth, averaged over a range of latitudes. And here is the change of temperature due to the change in the solar radiation. And from the surface of the Earth to the atmosphere, and from North Pole to South Pole. With the change in the solar radiation increase, both the lower atmosphere and the upper atmosphere will be warmed up. However, as we just showed and predicted by Manabe in the 1960s, that with an increase in greenhouse gas such as CO2, the lower atmosphere will get warmer, but the upper atmosphere will cool down. And here is the prediction of temperature change due to greenhouse gases. So you may wonder, what does our observation look like? And here shows the observations of temperature change using satellites from 1979 to 2018. Although the scales of the two plots are different, but we can see the general patterns of warming in the lower atmosphere and cooling in the upper atmosphere, which is more consistent with the effects of greenhouse gases. With that, I'm going to talk back about myself. So I was asked to talk a typical day of my life, but a day of my life is just like weather is chaotic and hard to predict. So I plan to give a summary of my working life. So I tend to work more focused in the morning, so which includes writing papers, play around with data and trying to understand the data, and writing codes to analyze data. And in the afternoon, I will go to some regular seminar, but I also randomly walk into colleagues to discuss with them. And I also read papers from the literature. But if you look back a few years, my life is also occupied by teaching and being taught. And I'm also involved in a few organizations. in the physics department, including GASP, CO prime, and R cube. And I'm also in a few mentorship programs to share my experiences with others. With that, I'm happy to take any questions. Thank you. Oh, my advisor? My advisor is Mike Riswell, as I showed in the first slide. Yes. Sure. I mean, like this. Sure. So the question is, what does the gray color in this plot mean? As we can tell from the color bar, gray means the temperature changes little from 0. So it means there's basically little temperature change.
On these plots, I was wondering how different actually are the observations from the predictions? Because the scale you said was a little different, but like, are they actually pretty well, are they close?
Yes, so the question is, how does the scales in the observation predictions differ? So here shows the scale of 0.4 degree per decade. And here is the total linear change over this range of time. So strictly speaking, they're not comparing the same thing, but I think a better example is to take a look at this prediction made in 1989. So here you can see the scale is about a factor of 5 larger in the prediction than in the observations, which is due to the fact that only one factor is considered in this prediction. Only the change in CO2 is considered. But in reality, there are many factors, both natural and human, that will affect the change in temperature. And the current models, I would say, predict very close to the observation. And no, I don't have slide. Yeah, that helps. Yeah.
What are some of the proxies that are used to get the temperature from before we started measuring?
Yeah, that's a great question. Yeah, so the question is, how can we reconstruct the temperature of the past? And here I just showed 2 examples here. In the left here shows an ice core, which, for instance, are found from Antarctic. And here you see that these different colors actually represent different seasons. You see these lighter colors denote summer times. And there are also air bubbles trapped inside ice, which you can use to get information about the temperature. To be more specific, you can look at the ratio of isotopes of oxygen, and the different isotopes of oxygen will have slightly different density, so they will condense to ice more or less differently, which gives you information about temperature. And another way is to look at tree rings. That you can look at the growth of the tree ring. So, so for instance, here shows summer wood and spring wood, and there's a drought happen. It's a great question.
So in terms of the flat of carbon emission cuts, and those say that the war has to be this carbon by 2030 or 2030 or 2050. Is that a given what you have known about how would you say is our, let's say, time do we have? So, like, save time.
Yeah, so the question, and please correct me if I'm wrong. So the question is that we observe the increase in CO2 and also in temperature. How much time do we have if the CO2 is continued to be emitted to save our climate? Is that your question?
Yes.
Yeah, so
So how long do we have until there's very massive substantial changes that can be absorbed in the daily life that irregular people don't?
I think we already noticed that in terms of the frequency of extreme events that have affected people's lives. If you are talking about like past a point, there is nothing we can do to save the climate. Then first I have to say the prediction is very hard, especially about the future. But I believe the current consensus is about 2050. 2050.
Then what's going to happen after?
So the prediction is that past a certain point, it's very hard to turn the system back. And so there will be, as I just talked about, water vapor feedback, that you'll warm up the surface, you'll get more water vapor in the atmosphere, and more water vapor will further heat up the surface. So at a certain point, all these feedbacks will be will contribute together to make the process irreversible.
How worried should we be? How worried should we be about such circumstances in which there's it has the equilibrium of there's no turning back. So how worried should we be?
I think that's not a question I have a definite answer to, because given the exactly same information, your reaction is totally dependent on you. And what I do and my aim of my talk today is not to.
Like, how would it affect, say, would there be like a mass extinction, for instance? And in that sense, would there be a shortage of any resources? Would there be any, let's say, effects on certain industry? Okay, that is, so if that actually happens, that the temperature is increasing, what is going to happen to basically the Earth? Aside from the interesting increase.
Yeah, so the most direct impact is perhaps ice will be melt and the sea level will rise. So the cities, near the coast will be affected the most. will there be mass extinction? I would say it's possible, but I can't give you, numbers about how likely it will happen or how alarming you should be, because that is your decision. And what I'm showing here today is to give you the information, and the decision is totally up to you.
Well, if you have more questions for Shane, you can stick around afterwards and talk to him. Otherwise, there is a feedback form. We'd love to hear from you about how you thought this talk went. You can scan that QR code right there, or just use that tiny URL that's listed on the slide. Yeah, let's thank Shane one more time.